What's encryption? Word gets bandied about an awful lot today. What is it?
Like a way to safely secure data.
In one way, yes. Originally, it was simply to secure messages, right? So I'm going to store your data somewhere. I'm going to store this information. I'm going to send this information to someone. So I take a regular piece of data, my plain text, and I encrypt it. And that gives me something called the ciphertext. And that's what I store or send or use as publicly displayable. And the whole idea is that that's hard to get information out of. The ciphertext should be complicated so that you don't know what information I put in it. If I then go to need that information or change it or do something with it, I need to decrypt it to get back the plain text. So whatever thing, method, function I'm using to do my encryption needs to be invertible. A Christmas Story. Now you've seen the movie A Christmas Story. What's he saving up for? That's what he wants for Christmas. What's he saving up for? Save your box tops. Yes, he wants the Red Ryder beating up. He wants that for Christmas. What's he saving the box tops for?
Is it a weekly thing?
Yeah, every week.
He would like listen to the radio for then the subway code for his like cowboy thing, something like that.
There was a decoder ring, right? And the decoder ring, he had to save up all the packages, and they would send the message, and he would be able to decrypt them, send the key, and he'd be able to decrypt the message on the back of the box because he had a decoder ring. This one's from the National Spy Museum in DC. And the way this works is based off of the Caesar cipher developed, I hope to nobody's surprised, by Julius Caesar. Take the message you want to send and convert it to the numbers from 1 to 26. So I need to know the numerical positions of the letters of the alphabet. If I think about it that way, in numbers. But what Caesar said is shift every letter forward 3. So I'm going to take my decoder, and I'm going to say, oh, on the outside ring, I'm going to align A with D. That means everything's been moved forward 3 spots. So my message, hi there, on the outside, H goes to K. I, on the outside, goes to L. T, on the outside, goes to W. H, we already said, was K. E goes to H. R goes to U. E goes to H. And that's the message I sent. And then if you want to decode this, you back everything up 3. And now on the outside, K becomes H. This is the simplest encryption shift we have. And if we do it in numbers, we can think of doing this addition and subtraction mod 26, because the alphabet wraps around. Ben, do you happen to remember what the secret message is that he decodes every week? When he finally gets this decoder ring?
Like, something like brush your teeth or something stupid like that.
He was saving up Ovaltine box tops. The message is drink more Ovaltine. This particular ciphering, again, goes back to Caesar, but was made problematic by the fact that all you really are doing is changing which letters are which, and if I know what the most frequently used letters are, I can break this. The most frequently used letter in the English language is. Unfortunately, no. It is. Gives you 4 more to pick from. I'm sorry? It is E. As a matter of fact, the first 10 letters in order of frequency, I'm sorry, the first 12. And the only reason I remember that is because there was a sci-fi story, and that's the title of it, about a printing press that became self-aware because it kept getting fed all these more frequent numbers. It was one of the early AI stories. So the most frequent letter I run into is E. So all I have to do is go through this message and make the assumption, if I have a large enough sample, that statistically the most commonly appearing symbol should be E. And work my way down in frequency. How many of you saw The Imitation Game? The Alan Turing story. The Germans had a very complicated ciphering machine. How did they break the German ciphering machine? Because they reset the code every day. And it wasn't just one code wheel, it was multiple code wheels. It was a variation of something called a Vignere cipher. So instead of just using a single number, we use code word. So I'm going to take a fairly reasonable message. Thursday. And I'm going to say, I want to encode this message. But instead of just using one shift, I'm going to pick a code word. My code word for today is blue. And now I'm going to do this numerically. I turn each of these into the number of the position of the letter in the alphabet. I wrote this down earlier, so I don't have to try and do it in my head. But I'm going to go mod 26. So that means A is 0, and I'm going 0 through 25. And I do the same thing for my code word. And instead of just adding 3 to every number, I write down the code word under each of my numbers. And I add mod 26. (22, 18, 13, 19, 33. 33 mod 26 leaves me 7, 10. And this, I switch back to letters, becomes my ciphertext. So instead of sending the message, snowfall is coming, I send this message. That's intelligible, isn't it? How do you decode it?
Would you change those back to the numbers and then subtract code word and then?
Revert back, right. All I have to do is undo this exact same operation, but it means I need to know the code word. And I need to, or, instead of knowing the code word, I need to know its inverse. But its inverse, again, is mod 26, right? So mod 26, -1, is 25, right? -11, 15, -20 is 6, and -4, mod 26. So there's my code word. Z, T, G, Y, X, W. So I could send somebody this code word, they derive this one, and then they could do adding again, or they could simply subtract from each one. Either way, the arithmetic is the same both ways. This was slightly better, but how did the German Enigma machine fail? Well, there was something they were absolutely sure was in every single message. Every message the Germans sent in World War II ended the same way. Every one of them ended with a salute. The last 10 letters were always Heil Hitler. So I knew what those letters were. I could use the decoding backwards, figure out the keyword. If it was less than 10 letters long, and they'd actually captured a machine, and they knew the lengths of the code words. But that meant they had to do all of this analysis in less than 24 hours to be able to decode that day's messages. The machine was reset every night. These are simple substitution ciphers. There were physical ciphers. Why did George Patton carry a writing crumb? Seriously. In World War II. Writing crumb? Come on. It was a holdover of a marshal's baton. In the Roman legions, in the Chinese armies, field marshals had a baton indicating their rank. It was usually decorated, some sort of tassel from Caesar, emperor, whoever. They had an insignia. But what's more, they were different diameters. Why would that be important? Because the guy in charge had all the batons. He could take a strip of paper, wind it around the baton, and write the message. Then unwind it and send that. If you intercepted it, how would you know what was written on it? You'd need an object to wrap it around of precisely the right diameter. And every field marshal's baton was a different size. You'd have to know who the message was intended for and what size the baton was. So it was a holdover, a mark of rank. I don't like doing this crap by hand. So what I need is a function that's easy to compute. Throw in my technology, let it do the computation. Something that's easy to invert, so I can get the decryption key. And I would like it to be difficult to decode without the key. These are usually referred to as trapdoor encryptions. They're easy to get into and hard to get out of. Well, it turns out that the basis for almost every modern encryption algorithm is Fermat's little theorem and Euler's generalization. So you have in your hands right now all the tools we need to develop an encryption system. 3 guys, Ron Rivest, Adi Shamir, and Leonard Adelman came up with one that now bears their initials, the RSA encryption. If I have 2 reasonably large prime numbers, now when I say reasonably large, I mean, I don't know, 100 digits long. Large. Because I'm going to do this on my computer. It's fairly easy to multiply them together. But on the other hand, if I give you PQ, given P times Q, finding P and Q is hard because factoring is a bitch. Unless you happen to have small primes in your number. I asked you to do abelian groups of a particular order. I've forgotten what the number was at this point. But you know, it was divisible by 5 or 3 or something small, right? So I could get these numbers factored easily. If I start with 2, even 5-digit primes, we'd be here for weeks trying to figure out what the hell the products are, wouldn't we? Without a technology piece in front of us. And if I use 200-digit primes, even with technology in front of me, factoring that giant product is a major pain in the ass. Because large prime numbers are very sparse. There are a lot of composite numbers. There aren't very many large prime numbers. So what? Why does that help me? Let's start with 2 prime numbers and take their product. Let's pick another integer, relatively prime to that product, which means it's not a multiple of P and not a multiple of Q, but more. I want a power congruent to 1. I'm going to run out of room here. I'm going to move that down here. W congruent to 1 mod the product P minus 1, Q minus 1.
Where the hell is this going?
Then A to the W is congruent to A. Mod N. Sure it is. Right. This is the backbone of the RSA encryption algorithm. This right here. So let me start with the modulus. W congruent to 1 mod the product P minus 1, Q minus 1. That means that W equals something times P minus 1 times Q minus 1 with 1 left over. So when I take A and raise it to the W, and I go mod, my brain says what I should be doing is mod N, right? What's Euler's theorem tell me about working mod N? Come on, people, this was Thursday.
The greatest common divisor of any one is greater than 1, then you can have W is equal to any relative prime number to between relatively prime number less than n in relation to n.
And then what happens?
A raised to that power is congruent to 1 mod n.
So here's the $64,000 question. What's phi of n? Oh, wait a minute. N is the product of two primes. So let me see if I can figure this out from a couple short examples. Let's go with two different prime numbers. We'll use small ones. How about we use 2 and 5? I think 2 is too easy. Let's use 3 and 5. How many numbers less than 15 are relatively prime? To 15. How would you find how many numbers are relatively prime? Reese?
Just like list the numbers from 1 to 15 and then cross out whatever is not.
Sure. But I'm going to do that in two different ways. I'm going to make that list, instead of just one big list, I'm going to make 3 rows of length 5. And I see each row ends in a multiple of 5, doesn't it? So those numbers get thrown out. 5, 10, and 15 are all gone. And at the same time, if I make 5 rows of 3, all of these numbers are multiples of 3, they get thrown out, don't they? Huh. Reese, how many numbers did you come up with?
9. Relatively prime.
9. What were they?
1, 2, 4. Wait, 6 is not. So 7, 8, 11, 13, 14 value.
Which gives me 8 of them, right? Hey, wait a second. If I just think of this, and by the way, let's exclude 15 for the moment, because I know it's never going to be relatively prime, right? There are p minus 1 multiples of p in this list. Sorry, p minus 1 multiples of q in this list. There are q minus 1 multiples of p in this list. So I know how many numbers I need to throw out. I need to throw out the p minus 1 numbers, and I need to throw out the q minus 1 numbers. So phi of pq should be all of the numbers up to pq except pq itself minus p minus 1 minus q minus 1. Yes? I have to throw out these p minus 1 numbers, and I have to throw out these q minus 1 numbers, and I crossed out that one from the total PQ. All right, wait a minute. I'm subtracting a subtraction. That makes this one, -1 and this -1 cancel out. So I end up with PQ minus P minus Q minus a minus becomes +1. Ready for the best part? That factors. So Reese, I actually got 8, and that's why I jumped so bluntly when you said 9, because what's phi of 3? And phi of 5? 2 times 4 is 8. Okay, wait a minute. My goal back here was to do a to the w, right? W looks like this. So Switching back, a to the w is a to the k times p minus 1 times q minus 1 plus 1. Just like we did with Fermat's little theorem, with Euler's theorem, I'm going to break that up. That's a to the p minus 1 times q minus 1 times k times a to the first. In that first term, I've got three numbers being multiplied. I'm just going to look at the k. I'm really multiplying thing times k. I'll make that power of a power. And then I just have a to the first. What happens when I mod n? Euler's theorem tells me
Just off with M on it.
because the thing inside that parentheses is 1. Holy crap, wait a second. I just found my encryption and my decryption. The two primes I need are P and Q. And then I need a number in that range between 1 and P minus 1, Q minus 1 that is relatively prime. And I'm going to use R as my power. What's special about R in the universe Z P minus 1, Q minus 1? This is an abstract algebra question. The answer is something having to do with that ring.
unit.
It most certainly is, because its greatest common divisor with the modulus is 1. And if it's a unit, it has a multiplicative inverse. I'm going to say that R times S is congruent to 1 mod P minus 1 Q minus 1. So my inverse is S. So the way the encryption works is you tell people two numbers. You tell people S, and you tell them the big encryption number PQ. And then in your back pocket, keep private R. Keep that one hidden. S is the encryption key. And R is the decryption key. So, how does this work? You have a message. You turn it into a string of numbers. I'm going to assume for the moment that the message M is between 2 and n minus 1 as a number. Because if it was n when I did mod n, it would be 0. That's not helpful. If, by the way, your message is bigger, chop it up into blocks. Remember, you have the power to send more than one encoded word at a time. So you take your message and you compute that. Y is your ciphertext. Your plain text message M, this big number, has now become a different number. Y. So I get the message. I get Y. How do I decrypt it? Oh, I do Y to the R. Because that's the same as M to the S to the R, which is the same as M to the RS, but RS is 1. By the way, on my computer, the number of bits of security. You go visit a website, you're going to go buy something, that little lock shows up on the website. That little lock stands for This is encrypted. We're going to hide your credit card information. Secure Socket Layering, SSL. It's the encryption protocol. And the size of the encryption algorithm is based on the number of bits in the primes that they use. Currently, SSL uses 4096-bit primes. That's 12,000 digits. And not small numbers. All right. It's all well and good for me to talk theory. Let's do one. Okay. In order for me to have an encryption setup, I need to know that R is relatively prime to P minus 1, Q minus 1, and I need to know what its inverse is. Grab your calculators. What's 43 times 59? Trust me, get your calculators out. You're going to need them for the rest of the class. I'm sorry? So use your computer. You're sitting in front of it. There's a calculator on there. Use your phone. I don't care. I need a calculation device.
2537.
Great. And P minus 1, Q minus 1 would be 42 times 58 is
2436.
okay. I need to find the inverse of R in Z 2436. Now here's where I say, you've done this before. Because in order to do this, what you need to do is find the greatest common divisor and then work the greatest common divisor backwards. We did this in discrete. We called it the Bézier coefficients in the extended Euclidean algorithm. So that's what I want to do here. I want the extended Euclidean algorithm. This is why we do most of this on the computer, because the following process is not short. So, to do the Euclidean algorithm, I do divisors. I do 2436 is something times 937 with something left over. I need quotient remainder. Keep going. I move the 937 over to this side. It's something times 562 with something left over. We keep going until we get either the greatest common divisor, and since I gave you R, I know I should have set it up so that the greatest common divisor is 1, or I get 0. So let's keep going. 1 and 375. So 562 is some number of 375s with something left over. And again, that's a 1. 375 is something times 187 with something left over. Ooh, 187 and 187 is 360 and 14 is 374. The remainder is 1. 2 times 187 is 1 left over, which means when I do 187 is something times 1 plus something, that's a 0. And that tells me to stop here, and the previous remainder is the greatest common divisor. Now I need to work it backwards. I'm going to start with 1. And I'm going to say, oh, 1 is 375 minus 2 times 187. That's this row right here. I just moved the two 187s to the left. But 187 was the remainder here. So let's write it as 375 minus 2 times 562 minus 375. There's only one of them, so I don't need to put a coefficient in front of that. Hey, wait a minute. I'm going to regroup without simplifying. I'm just going to regroup. That's 2 375s and another one. That's 3 375s minus 2 is 562. So that used the remainder 187. Go to the next line up where the remainder is 375. And let's use that line. 3 times 937 minus 562 minus 2 more 562s. Again, I regroup without simplifying. So I have 3 times 937 minus 3 and then minus 2 is minus 5, 562s. With me so far? Kind of, maybe. Don't see the point of it yet. One more remainder. 562 is the remainder in this first line. Replace 562 by 2436 minus 2 times 937. Because that's what this would be if I solve for the remainder. Now I got the two numbers I was interested in. I've got 937, that's my R, and I've got 2436, that's my mod. So when I distribute, oh, I forgot to write down the 5. How many 937s come out of this part? Plus the 3 more gives me 13 times 937 minus 5 times 2436. Hey, wait a minute. This number, 13, that's S. Again, grab your calculators. What's 13 times 937? 12,181. That's something times 2436 plus something. When you divide 12,181 by 2436, your quotient is your quotient.
Oh, quotient.
Your quotient is 5, your remainder is 1. Because my quotient is 5 and my remainder is 1. I found S. So I know what I need to keep hidden in my pocket. I need to keep the number 13 hidden. No, sorry, I need to keep the number 937 hidden. And I tell everybody, if you want to encode a message to me, you need to raise it to the 13th power and mod it by PQ. What was PQ? 2537. So I need you to visit a website for me. Go onto Google and Google big integer calculator. Because we're about to do some very large calculations. The one I'm used to is the second result in the links. Looks like this, big integer calculator. And notice I have addition, subtraction, multiplication, mod, square and mod. I have a lot of options right here that I can use. So I'm going to send a message. And I'm going to make my life easy. And I'm going to send a short message for the moment. The message I'm going to send just says stop. Plain text. I need you to do me a favor. If A is 0 and Z is 25, what is the letter S?
18.
T then is 19. O is and P is right after that, so that's 15. Now remember, my number is 2537. The number I am using for the mod is 2537. So I'm going to break this up into 2 blocks. I'm going to send 2 4-digit numbers. To encode these numbers, I'm going to take 1819, raise it to the 13th power, and then mod by 2537. Now, there is no way on God's green earth I'm going to do that by hand, so out comes my giant integer calculator. And I say, okay, X, 1819, Y, 13, and I'm going to do X raised to the Y, which is this option right here. And it spits out this giant answer, which is, by the way, 43 digits long. No way I could even do that on the calculator I have. And I'm going to make that number my new X. So I'm going to say, take M, my answer into X. Then I'm going to replace Y. What am I modding by? 2537. And then I'm going to hit X mod Y. 2081. That's my first block of ciphertext. Now I want you to do it again. 1415 raised to the 13th, mod 2537. Okay, question for you. If you intercept the message 20812182, if A is 0, how do I do 81? Mod 26. So What are these letters? $20, working backwards. Z, Y, X, W, V. Remember, Z is 25. We're going 0 to 26. So Z, Y, X, W, V. So this is V. And that means, by the way, 21 is W. 81. What's 81 mod 26? It's almost a radio station. WDV. You get this message, you don't know what I'm saying, do you? This is as clear as mud. Useless information. Congratulations, you've intercepted a message from me. But you can't tell me what it means.
Didn't we say T is 19, so shouldn't 20 be U?
Z, Y, X, W, V, 25, 4, 23, 22, 21. You're right. UDV, even more helpful. UDV. What's UDV mean? But I have in my pocket the magic number. How do I decode this? I use this number. So I'm going to take these two pieces and I'm going to say, hey, wait a minute, out in public that everybody knows, use 2537. So I'm going to say, okay, I take this number and 2537. So I take 2081, raise it to the 937th power, mod 2537. And I do the same thing with the other block, 2182 to the 937, mod 2537. And that's why I am absolutely not doing these calculations by hand. I'd break my calculator. I'd break my head. Raise something to the 937th power? You out of your mind? If this first result isn't 1819, I have a problem. (2081) raised to the 937th power, by the way, is 3,100 digits long. Put that in X and mod it by, oops, damn, wrong button. Try again. 2081 raised to the 937th. Put that in X, mod by 2537, mod 1819. I got ST. But can you imagine sitting there trying to decode this with no idea what the correct inverse is? Now, these numbers are small enough. You could go through and figure out 937 the same way we figured out that the inverse was 13. These numbers are small enough, I can do that by hand. But it's tedious as all shit, isn't it? And so by doing this on a computer with 12,000 digit numbers involved, there's no way you're going to break that code, are you? When you see that little lock, you can ask yourself, how many bits of security are they putting in there? How big are the prime numbers they're using to encode? How well does this work on my bank account? Notice that my passcode was fairly small, right? The code that lets me in. So when I go to the ATM machine, so the ATM I here, zip, I don't have to enter a 4-digit number. I only have to key back the encryption. My passcode is much smaller than the encryption code itself was. Again, I could do these powers faster. If I'm willing to spend my time doing the modular exponential algorithm. Here, let me remind you of this. 2015 raised to the 17th power mod 3,233. If I want to do a calculation like this is going to suck. But I say to myself, wait a minute, 17. What's 17 in binary? Binary. All I'm going to do is square. What's 17 in binary?
0001.
1, no 2s, no 4s, no 8s, and a 16. 1, 0, 0, 1. Looks like this. 1, 0, 0, 0, 1. Okay. So really, I need 2015 to the first, and then I need 2015 to the 16th. But I'm only going to get there by squaring. These numbers are small enough I can do them on my calculator, but you can still use the website. What is 2015 squared? Mod 3233. That's what I got too. So if I want 2015 to the fourth, that's the same as 2810 squared. So I can square again mod 3233. What do you get? (2015 to the eighth is 1114 squared. So 1114 squared, divide by 3233, take off the integer, and multiply by 3233. My remainder is 2757. So one last time, 2015 to the 16th is 2757 squared. What do I get for this number? Which means to do the calculation I want, 2015 to the 17th is 2015 to the 16 and 1. That's 2015 to the 16th times 2015 to the 1st. But since I'm working mod 3233, I can use 266 here and 2015 here. And then I just have to do one multiplication. 2015 times 266, and take this number, mod 3233. By the way, that's not how the big integer calculator works. The big integer calculator actually does the entire multiplication, but no way in hell am I doing that by hand. All of this encryption boils down to the fact that it is hard to factor the product of two primes. So factoring n is a pain in the ass. What's the problem with this? The problem is the computers keep getting faster and better. The original developed idea with Euler's theorem as a tool for encryption goes back to G.H. Hardy, who in the mid-1800s said that this type of number theoretical experiment was beautiful and elegant and utterly useless, because no one would have any need for this kind of huge number crunching. This calculation takes upwards of a week, because his fastest computer was an abacus and a pen. Even Babbage's original calculators, the analytical engine and the difference engine, couldn't do this type of mathematics at all. They weren't powerful enough. They didn't have the calculation ability. Your laptop does 2.6 billion operations a second. If I tell it to factor a 6 or 7 digit number, it'll be done in under 10 seconds. Probably even under 1 second, depending on the way you write the algorithm. I ask you to factor a 12,000 digit number. Well, it's probably going to take a little longer. It's going to take long enough that I will have flushed the result out of the memory of the computer that received the information for your credit card, and thus is not stored anywhere. Although, Hayden, if I do store the information, I better make these even bigger numbers. If the computer scientists are correct in developing a quantum computer, all of this goes out the window, because quantum computing's main goal is to break the complexity of factoring. Because right now, factoring is an n factorial problem, big O of n factorial. And quantum computing is designed to take non-polynomial difficulty problems and break them into polynomial time. And that means that that impossible to factor number might very well be doable in minutes. Terminator 2. Anybody see Terminator 2? No, you're looking at me like I'm a space editor. In Terminator 2, the child protagonist, played by Leonardo DiCaprio, is hacking ATMs by brute forcing the password, the PIN numbers, out of people's cards. He's got a skimmer set up on an ATM. He captures the account information, but not the PIN, so he's brute forcing his way through the PIN, which works. And he does it in about 5 seconds. because he runs a brute force algorithm on his computer, and there aren't more than 10,000 numbers to pick from. What happens when we get computing power enough? This goes away. So there are other encryption algorithms out there that are linear algebra based, that are higher group order theoretic based, that actually are more complicated and are worth investigating in a graduate course on cryptography. Or if you want, there is an MAA presentation on cryptanalysis available on the website and on the playlist that I think I linked for this class in our web links. Have a wonderful day, people. I will see you all on Thursday.
Question.